Hi everyone, welcome back and thank you for being here after your lunch.
Welcome.
Welcome, yeah, it's kind of hard time to be here, right? But well, anyway, here we go. So I'm Sebastian Garcia. Again, if you were in the morning, you remember me from the bathroom probably. But here I am now as part of the university in our research in Stratosphere project.
The name of the talk will be Detecting Malware Even When It's Encrypted, Machine Learning for Network HTTPS Analysis.
First of all, who here in the room is working in machine learning? Working in machine learning there? Okay, who in the room knows what machine learning is? Oh, there you go. Who in the room is using machine learning in everyday applications, tools, whatever? This is tricky, right? Because actually all of you, if you're using Facebook, Twitter, you're using machine learning every day. You don't know, and maybe this is good, right? If you don't notice, good for them. Okay, maybe not good for you, good for them. But yeah, it's being used all the time. So in the Stratosphere project in the Czech Technical University, we are doing several research. And this one is, hey, we have malware is encrypted. We need to detect this malware in a very, very accurate way without knowing what it's inside. HTTPS, so Google, in this case, the first image, and that one, it's the Let's Encrypt website. They are, both of them, keeping track of the web pages in the world that they are being encrypted. So if you see here, actually, February 24 this year, 82%, I will read it because it's super small, 82% of the traffic going through Chrome is encrypted. And in the case of Let's Encrypt, they are estimating that approximately 85, 80 is also being encrypted of all the web page in the world. So you know this is a trend, and this is so much a trend that in April, Chrome will start putting to any website that it's not encrypted, not secure, which is a huge step. Now, if you're not encrypted, by default, you're not secure. So we are hoping going to a world where we are going to be encrypted kind of 100% of all the traffic in the web, right? Not all the internet traffic, only in the web. So what about this and our research? Malware, what about malware? So we have malware threat intelligence analysts in the room, malware analysts in the room, there. Network traffic security researchers, network something, using networks. Oh, there you go. Come on, give me something. I was like, so malware, what's going on with malware? Okay, the thing here is that this is encrypted, right? So we don't know. That's the truth, right? That's why it's encrypted, because we don't know. So we can estimate something. We have here some estimation from Cisco. They're saying in 2016, they're saying 10 to 12% of the malware uses HTTPS. In June last year, the people from Siren, they're saying, hey, 37% of all the malware uses HTTPS. This is hard to measure. Actually, it depends in which samples you are looking, right? So it's not straightforward. In our own research, in the Stratosphere laboratory, we have a Nomad project for analyzing HTTPS malware. We are executing HTTPS malware all the time. Actually, you can go and download. Everything is public. And we found that from all the malware that it's using HTTPS, so we already know, because we are looking at the traffic, we say, hey, that's HTTPS. From all that malware, 97% uses port 443, which means that there is a lot of malware there encrypting and not using 443, which is super interesting. And from all this traffic, 87% uses TLS, which means that 13% of the malware it's encrypting without TLS or SSL, which means custom encryptions. So it's not straightforward to say, yeah, malware uses HTTPS or does not. When, how, right? And more importantly, once you open the traffic, because we are having man-in-the-middle proxies for opening the traffic, when you open the traffic, you see what the malware is doing, and you find that not everything is an attack. So yes, the malware is using HTTPS. What for? Maybe it's just going to Google. Maybe it's going to some website for checking if internet is there. So this is not part of the attack. So from all the traffic that the malware is doing, the amount of traffic that is really the command and control or the malware doing some attack is far, far less, okay? So it's difficult to say 80% or 20% or something like that. So, however, encryption sucks, right? Because, hey, we cannot use our classic detection tools. IDS is Bro, Snort, Suricata, anyone? SRO, Suricata, no, Bro, IDS is. So if you want to use fingerprints, if you want to use signatures, you cannot, it's encrypted, and then you say, oh, what should I do?
So one solution for this problem is TLS inspection. TLS inspection is some hardware which is put in the middle of the traffic, for example, in some factory, some proxy server with his own certificate. And what is task for this interceptor? So his task is decrypt the traffic, decrypt the HTTPS traffic, scan for the malicious, and then again re-encrypt the traffic and send to the destination place. This has some advantages and disadvantages. First, the advantage is that you can use the classic detection method because finally the traffic is decrypted. But there is a lot of disadvantages. For example, it's expensive because you have to buy some hardware, you have to buy something. Next, it can be slow because you have to decrypt the traffic, scan for the malicious, and then decrypt, re-encrypt again. And finally, there is a problem with idea of HTTPS. The idea of HTTPS is privacy, so in this case, it's not like this.
And finally, you can imagine that anyone here in the room is using TLS interceptors in the routers, in the companies? No? So this is very common, right? Like your company wants to know what you are doing, so they're opening your TLS traffic, and that's it. They can see what's inside. So the problem with doing this is that for opening your traffic without you knowing, they have to install in your computer, device, cell phone, the certificate they will use for opening this and telling you, oh yeah, I am Google, when they are not. So you should trust this. So they're installing this in your computer. Maybe you know, maybe you don't. It doesn't matter. You sign the contract, so they can do it. So the thing is that doing this, and usually you have errors like, oh yeah, no, it expires something, trust, don't trust. You are teaching the users to click on, yeah, I don't care, this page is like the certificate expire, and go anywhere because I know there is something in the company going on, just click and access. You are teaching your users not to be mindful of the security. Now they know that anybody opening the traffic is kind of okay, right? It happens. And this is bad for our community, right?
Okay, so next solution, it's our goal that we would like to detect the HTTPS malware traffic without the decryption. What does it mean? Does it mean that we are not able to use the proxy server, some interceptor, but we have to develop some new features and methods which will be able to detect the HTTPS malware traffic with high accuracy and low false positive rate.
Remember, this is a machine learning project, right? So this is what we want to do. We want to go there and find this out. So, oh, this is mine, sorry. So what is TLS, LSL? So what is the difference between SSL and TLS? Anyone? TLS is newer, good enough. And that's it, right? They just change the version and keep updating the protocol. SSL, old, TLS, good, SSL, bad, let's say, roughly. So the idea is that you want to encrypt. Actually, you can encrypt any type of connection. In the case of HTTPS, it's HTTP, but you can encrypt anything. In this case, client saying hello. The server is saying, hey, yeah, this is my certificate, and these are my parameters. And then I check if the certificate is trust or not. I create a symmetric session key, like AES, okay? And then I encrypt the asymmetric public key with my symmetric key. So anyone knows why we are doing this? Why we are generating a symmetric key to encrypt the asymmetric key? performance, right? Like all these public and private key exchanges are super slow. I mean, orders of magnitude. So we use asymmetric key encryption only for exchanging the symmetric key. And when we both share the symmetric key, there you go, we encrypt super fast. Another question, the fact that the server should or must send me the certificate, is it mandatory? Can I connect to an HTTPS service and not being given the certificate? Usually it's weird, right? Because without the certificate, we cannot encrypt. And most tools and most interception hardware devices, they're expecting the certificate. However, Chrome, especially, I'm not sure Firefox now, I don't know, Chrome at least, they are doing a cache of the certificate. So if they already have the certificate, they are not transferred it again. And we find this the hard way, which means František was looking at the traffic all day. This is what he loves to do. I cannot stop him.
I love it.
And he was like, hey, there is no certificate in here. I said, no, I'm pretty sure we are missing it. And then there was no certificate. In a lot of connections, because Chrome already has it, you are not seeing the certificate, which is super weird when you're analyzing. So yeah, there you go, and then you decrypt everything, and the server and the client encrypts everything. The certification part, so you have a certificate, you are google.com or something like that, in this case google.cz, and you have your certificate, and somebody's trusting the certificate, so he's signing it for you, and then somebody else is trusting the certificate of Google Internet Authority and signing this one, and then, and this is like a pyramid, right? Like DNS, a trust hierarchy of relationships. So 2 questions in here. How do you get here? How do you get your new company about signing certificates to actually be able to sign certificates? How do you do this? Politics and something more. You need politics and lobby. You need to pay a lot, right? So you have the money, you pay Microsoft, Firefox, Chrome, Google. If you pay, you will appear in the browsers, because the thing is that the browsers have the authority to say, I don't trust you, or I trust you. So you pay, you are there. However, we are trusting these authorities, right? Right? No? Kind of is, we are. Anybody read about the scandal about the private keys leaked now in the internet? Yeah? So yeah, we don't trust them so much, right? So you can have issues with these certificates out there. So just be careful.
Yeah, it's important to realize after this that the privacy doesn't mean the security. So if you see in the browser the green color, so it doesn't mean that it's secure. It just means that your data between client and server are encrypted.
So for our analysis and our research, we need datasets. Datasets are hard to come by, so we just create them. In this case, we need pickup flows from HTTPS. We need malware and normal. We have 4 sub-datasets. We are using 163 malware and normal captures. This is one of screenshot of one of our VMs running the malware. We have a lot of them that are just running the malware, and we are checking what's going on, and again, and again, and again. So yes, we are having here 4 datasets that were used for the analysis. The CTU13 dataset is public. Malware and normal captures, 13 scenarios, a lot of malware, different malware, 600 gigabytes of pickup, free, go there, download it, use it for whatever you want. This is the first dataset that was including normal captures and background captures, which means traffic that we don't know what it is. Then we have the malware capture facility project led by Maria Jose Erquiaga from Argentina, and she executes 340 malware pickup captures, also downloading from free. You have them there. The third one is our own normal dataset. That means that František was there going to the web and browsing a lot of HTTPS traffic.
For 3 days.
3 days in a row, no sleeping. We don't allow him to sleep. Just clicking, clicking, clicking. Because we just wanted the certificates, right? We just wanted the communication. We don't wanted the behavior in there. So we have a lot of them as normal. We will see what normal means, because we are in here. He was using a lot of known sites, and then he was going to Alexa 1000. we will see there. And then the normal CTU dataset, this is normal captures from the university, not so public, but this is real people in the university sitting, working, and František was there. Hi, how are you? Hi, can I see what you're doing? Are you human? Are you normal? Can I see your computer? So he was verifying that these were normal people. And I'm not joking. Some of our laboratories have a lot of robots, and they were connected to the internet. So they said, OK, you're not human, so no, you're not in our data set. So these were real people that we know they are normal. And actually, this is harder to get than the malware. The malware, yeah, you go there, execute, cuckoo, whatever. Normal, how do you know it's real normal? Even if you're capturing your own traffic, how do you know you are normal? You are not infected, are you sure? And yesterday, and tomorrow, and 2 weeks ago. So the thing that what you consider normal or not is super hard, right?
So let's move to features, own features and the methods. The first of all, we have a pickup file with the packets, and we use the Bro IDS. I have to some small note that the Bro workshop is there, so it's a good tool. So. And we use the Bro IDS to generate the log files. Each log files describes something other. For example, connection log, describes the TCP connections. SSL log describes the SSL handshakes. And the fourth one, the X509 log, describes the certificates, or information about certificate. And DNS log are for our feature that we will use in the future. Yeah. So we have these three files we use, which describes our HTTPS connection. And from these three files, which describe one HTTPS connection, we create something what we call SSL aggregation. So in one SSL aggregation, we have all behavior and all information about one HTTPS connection. And from some set of SSL aggregation, we create the SSL connect unit. It's just our notation. And this SSL connect unit contains all SSL aggregation with same source IP, destination port, and protocol. So we have between 2 points for some client and to some server, we know all history of connections and the behavior of the client and the server. So this is a small example that we have raw data. It's not the most raw data. We have the pickup file first, but then this is the broad data in the files. And then we create the SSL aggregations, and from the SSL aggregation, we create the SSL connect unit.
So I wanted to say here that imagine that every time you connect to Google once, that is one connection, right? And then from that connection, František is taking the SSL and certificate together. So every time you click going to Google, that is giving us one SSL aggregation. However, we want to know how you are going to decide which is your behavior. So František is storing all your history between your computer and each server, Google, Twitter, Facebook, whatever. So this SSL connect unit can be days or weeks long. Every time you click, he's storing the certificate you use, the SSL aggregation you use, right? Again and again and again. So this is a high-level view of your behavior in time encrypting traffic.
And it's time for feature, because from the SSL Connect unit, we create high-level features. We have the 40. And it's mainly mean or standard deviation of some amount of some set. So I just describe a few of them because there is a 41 is too much. So for example, the first one is not so interesting. This number of SSL aggregation in one SSL unit. Then mean and standard deviation of duration. So each connection has some duration. So we compute mean and the standard deviation. Next, number of packets, mean and standard deviation again. Or the mean and standard deviation of number of bytes, or ratio of TLS and SSL version, or number of different certificates between client and server. So it can happen that there can be more different certificates.
And if you look at this, it's weird, but you can have multiple and different connections to the same server with different TLS and SSL versions, right? You can imagine this. The first time you connect to some website, it was using some TLS version, and the second time, it's using another one. So this is kind of weird, right? Like you change the certificate in the middle of two connections, right? Should not happen. However, remember that we are trying to separate malware HTTPS and normal HTTPS. And this is usually happening in the malware connections, right? The servers and the command and control channels, they're changing a lot, different domains, DGA. So there are some features that we capture the maliciousness, let's say, but looking at this, like the number of different certificates, right?
Another example is time difference, which doesn't connect it with certificate, but we have SSL aggregation, and we compute the second level time difference. So we have some time step for each SSL aggregation, and finally we compute how the SSL aggregation are periodicity or not, how much are periodic, let's say. Next, there is mean of certificate validity during the capture. So we have a certificate, and the certificate has some validation time, for example, 2010 to 2020. And also we have the day of the capture. So we have a date of the capture of the certificate, and we have the validity. So we can measure how the certificate is old. Maybe some malware can use the certificate which we captured one day before the end of the certificate. So this is too interesting, and we know that we have some certificate after the validity, before the validity, and we have a lot of them like this. So finally, we have a data model, which each line is one SSL Connect unit. And each SSL Connect unit has 40 features, and it has also the label, normal or malware, just the binary like this.
And these are being used for the training and cross-validation and testing data, right? This is the data to work with.
With this data model, we used this for machine learning algorithms. First one is XGBoost, which is very known in a lot of competition because he's very good for these competitions. It's extreme gradient boosting with the tree, with the decision tree. Then is random forest. It's random forest classifier with the multiple trees. Then we use the neural network. It's not our model. We use just the library, and finally the SVM.
So what we did is that we took all this data set. There is a complex process for splitting it. So usually you split it in training, cross-validation, and then testing. You take the testing data and you never look at it again until you finish. And then you work with the training cross-validation, which means that you are splitting it, different faults, and each time that you are iterating, you are training each model and then cross-validating to see how good it is. And then you are doing this several times, and at the end, you average all the cross-validation runs. Each of the model František was describing has multiple parameters, which means that you have 30 SVM model, 30 neural network, 30 random forest. So at the end, you're running maybe 100, 150 different models, and each of them you're running in a cross-validation of 10 faults, which is, I don't know, thousands of executions. So this is why it's taking so much time, right? So at the end, you take the best model after the cross-validation, and you go to your testing and say, OK, now give me the generalization error. Now tell me how good this model will be in a real case scenario. And in this case, we have two winners, let's say, the random forest and the XGBoost. The random forest with an accuracy of 95.65%, and XGBoost with 94.33%. However, you see that the false positive rate is quite high. 4% is super high. This is not so good for real-life implementation. Sorry, but for a first experiment, trying to detect this in a real network traffic, this is super good. We are very, very happy with the results. Not many real-life tools got these results in experiments. So these were real traffic, real normal people, real problems, and we have 4% false positive rate. And of course, we can tune this. We can get the values lower and of course losing a little bit of detection, but maybe it's possible. Imagine that 4% false positive rate means roughly that every 100 people, 4 of them you are saying you are malicious, and they were not. Which means that every 100 connections in your network, you are saying this connection is malicious, and it was not, which is a lot, considering that you have thousands of connections in a normal network, right? So these are results to improve, yes, but completely usable, especially in small networks.
It may be good to say which features were most powerful. So it was the certificate length of validity, how I showed that each certificate has some validity length. For example, 2010 to 2020. Next one, inbound and outbound packets in the connections. Next, validity of certificate, the capture. So I showed as well that we have some data of when we capture the certificate and we compare with the validation length. Next, the mean and standard deviation of duration of connections. Then number of domain in certificate. It's on DNS. I don't know if you know it. It's a part of the certificate, and there is a list of domains which belongs to this certificate. So, for example, in Google certificate, there is YouTube, Google, and so Google sees that, and a lot of them. Then there is SSL and TLS version and periodicity. So these 7 features were most powerful.
And I'm not sure now, but something like half a year ago, most of the malware command and control channels were using very old TLS versions, which was very easy to identify them. I'm not sure now, but especially because you can put them in Amazon or whatever. But yeah. So one funny part of, or amazing part of the research was that at some point we were checking, okay, give me all the certificates that were asked by the malware, and let's check if they are in Alexa Top 1000. And 50% of them were in Alexa Top 1000. And then we got the certificates used by our normal people, and only 30% of them were in Alexa Top 1000. Which is telling us that the malware is doing more things than only attacking. Like the malware, for example, every time it's loading some image, you are having a certificate from some website where the image is being downloaded. Doesn't mean that it's an attack. It's just some traffic from the computer. So be careful when you say, oh no, if the traffic is going to Alexa Top 1000, sure that this computer is not infected or this is not malicious. It may be, right? Not because the Alexa site is infected or it's attacked, only because the malware is doing a lot of things all the time, like phishing, downloading stuff, going to websites to get scripts. So it can be traffic from malware going to those Alexa. So the certificates used by malware are mostly, roughly, half from normal sites. That was a very nice conclusion for us.
Our conclusion, we had some results. There is a lot of things what to improve, like false positive rate. But I think it's good start to next research. And so there is a lot of features which we didn't check it, so there is a lot of work for future. But next, in the future work, we would like to use, how I said, next feature, for example, for the DNS log, or build our own architecture of neural network, because there's a lot of architecture of neural networks, but for the images, like segmentation, face recognition, but we were not able to find it some architecture of neural network for malware detection, or unsupervised learning, which is good when we don't have label data. So it's for us it's too difficult to label data. How Sebastian said, the normal it's difficult. So we would like to use and maybe try anomaly detection.
You can imagine that this was František's bachelor thesis, so he was working a lot, and he's moving on now. That's why he's wanting to go to their own architecture of neural network. We think that can be super valuable, maybe deep learning, we don't know. DNS traffic, of course. We are also migrating, we didn't say that, we are migrating also the tool for working to Suricata. It's already done, so we can work with Bro, Suricata. I don't know, let's see in the future. So I think that's it, right? So thank you very much.
Thanks for attention.